Okay. All right. So yeah, 8:36. I'll get started. This is discrete structures 2 for the last time this semester. We're here on April 12th. So an update. So assignment 3 is, not quite finished marking it yet. There was 462 submitted and there's 93 still outstanding. So I'm hoping it's done by the end of this week. And then assignment 4, again, I'm dropping the lowest assignment or shifting the mark or doing something with it. So if you feel like you're comfortable with your first 3 assignments, you don't have to submit it. And, obviously you got less help from the TAs for this assignment. So if you feel there's something not fair there, then, that will get dropped. But otherwise, if you hand it in, I'll get it marked as soon as possible, but that maybe a week or probably about a week. Otherwise, I think that's it. That's all the business, other than TAs might go back on strike or something. I don't know. That's out of our hands. We'll adapt, I guess, if that happens. But questions? Okay, so today is just a review class. I'm going to just review an old final exam, and yeah, that's it. Then at the end, and we might finish a bit early, but you can ask me other questions, or you can, if you've been looking at the old exams and you found a question that you need help with, I'll be happy to do my best to answer it. Maybe you can stump me. That's always fun. But yeah. So yeah, this is I give you all of this for the exam. So there's a few things that you don't have to look up. You're allowed to use calculators. And I think I also give you the definition of expected value, or one of them. The sum of k times the probability that x is equal to k. So this is my definition of expected value of x, and I think I put that on there too, just in case you forget. All right. So it covers everything, all topics, but I think I tried to slip a couple more questions, 1 or 2 more questions on expected value and random variables and indicator random variables. All right, so but just 1 or 2. So you're going to see everything. You might see slightly more of the stuff that you haven't been tested on yet, but not a lot more, just a little bit. So I will go through all of these questions, and then I'll kind of go through the first ones kind of quick, but if you have questions, just ask. And then when we get to the expected value and stuff like that, I'll slow down a little bit and go over it in a little more detail. Okay. So number 1, consider permutations of the set of numbers 1 through 10, for which all of the odd numbered indices have odd numbers, and all of the even numbered indices have even numbers. Okay, so how many such permutations are there? Well, I have, if I look at the subset of all odd numbers, of course, there's 1, 3, 5, 7, 9. So there's 5 of them. And there's also 5 even numbers. So I have exactly 5 odd numbers and 5 positions to put them in. And I also have 5 even numbers and 5 positions to put them in. So I would do, and let me make sure, just in case I get something wrong, I have, which one is this? Winter. Just to make sure I don't give you any false information. So what we would do here is the product rule. I would start with the odd ones. I have 5 locations, 5 numbers. I take all permutations. There's 5 factorial of those. And then my next task is to do the same thing for the even numbers. I have 5 even numbers and 5 locations, so I have 5 factorial ways to do that. And this is the product rule, so those are multiplied. So this would be 5 factorial squared, or C. Yeah. Number 2, consider permutations of the set of numbers 1 through n with n locations, for which A1 is less than A2. How many such permutations are there? So there's a couple ways to go about this. we did touch on the fact that if I have, well, for counting or for uniform probability, we sort of have the same effect, but basically, if I look at all the permutations for which A1 is less than A2, there's half of them, half of all available ones, simply because I can take all of the ones where A1 is less than A2, and then there's a bunch of permutations associated with that, and then I can swap them, right? So by symmetry, half of them will have this and half will have the other, and that's really true of any two locations, right? If I take two locations, one must be higher than the other, and if it's chosen uniformly at random, or if we're counting, then it's either probability 1/2 or half of them. So there's n factorial permutations, and half of them have A1 less than A2. So we get this. If I wanted to count it explicitly, I could say, well, I'm going to choose two numbers from my n available, and then I'm going to put the smaller of the two numbers in A1 and the larger in A2. So there's n choose two ways to choose the two numbers. There's one way to place them. And then I have n minus 2 factorial ways to take all the other numbers and arrange them. And then if I worked this out, if I expand my binomial coefficient, I have n factorial over n minus 2 factorial over 2 factorial times n minus 2 factorial. And these cancel out, and 2 factorial is simply 2. So I have n factorial over 2. So you can do it. If you're unsure, you can always resort to, the long way, but symmetry also works. All right, questions? Okay. Let B be a set consisting of 45 bottles, 17 beer bottles, and 28 cider bottles. Subsets of B that contain exactly 5 beer bottles and 0 or more cider bottles, or 5 cider bottles and 0 or more beer bottles. Okay, so we will say this is set A, and we'll call this, so let's say, we got a set B there, so this is kind of a pain. So this is A and this is C, so, and the OR means that we're counting A union C, right? So we're counting exactly 5 beer bottles and 0 or more cider bottles, or, which is union, exactly 5 cider bottles and 0 or more beer bottles. So the question is how many sets are, how many in A and how many in C, and then how many in the union, or sorry, in the intersection, right? So if I want to count A union C, that's equal to the size of A plus the size of C minus A intersect C, minus the stuff that we double counted. Okay, so the size of A, exactly 5 beer bottles. First thing I want to do is I want to choose my 5 beer bottles. These are subsets, so order doesn't matter. I have 17 to choose from, so the size of A, well, the first step is 17, choose 5. And then I have a bunch of, maybe some cider bottles, maybe not. I can have 0 or more cider bottles. I have 28 cider bottles total, so I could have anywhere from 0 to 28. So basically what I'm doing is I'm finding all of the subsets of the cider bottles, right? From 0 all the way to the complete. So the number of subsets of a set of size 28 is 2 to the power 28. So this is, So using the product rule, so I first select my beer bottles, and then I select my cider bottles. And then C, we can find similarly. We have 28 cider bottles. We're going to choose 5 of them. And then 0 or more beer bottles. So basically all subsets from my set of 17. So this is 2 to the 17. Okay, and then A intersect C. That means I have exactly 5 beer bottles and exactly 5 cider bottles. So the number of ways I can do A intersect C, well, let's just start writing this out. So this is 17, choose 5, 2 to the 28, plus 28, choose 5, 2 to the 17, minus, now I'm going to choose 5 beer bottles and 5 cider bottles. So 17, choose 5, times 28, choose 5. And do we have something that looks like that? Yeah, right here, right? So that looks like B. Yeah, B. Questions? I think these are the, some of the older exams have tougher questions because, well, McKeel taught it and he was kind of new to it. And then over the years, he kind of refined the questions to be not simple, but I guess more readily, easily able to do them in the span of a final exam. So yeah, a bit string is called a palindrome if it's the same forward and backwards. Okay. So how many, and what else do we got? N greater than or equal to 3 is an odd integer. So how many palindromes of length n are there? So if it reads the same forwards and backwards, well, I'm going to say, well, I'm going to choose something for B1, then I'll choose something for B2, I'll choose something for B3, and then I'll get to the middle one, which is, what is it? N plus 1 over 2. So this is Bn plus 1 over 2, whatever, it's the middle one. I think it's n plus 1 over 2. And then, well, the next one will be a reflection of whatever the previous one was. And then the next one after that will be a reflection of this one. So when I've chosen, basically my palindrome means I choose these ones, and that's going to decide the rest of the string. Okay, and this is a bit string, so I have 2 choices for each of them. And I have n plus 1 over 2 bits that I'm choosing, and 2 choices for each of them. So it would be 2 to the n plus 1 over 2. If you're like me, then that plus 1 minus 1 gives you a little bit of trouble, but you can always try it out on small numbers, right? So if I had n equal to 5, then the center one I know is 3, which is 5 plus 1 over 3, or over 2, sorry. So it is a plus 1, not a minus 1. All right, questions? Okay. Let n greater than or equal to 2 be an integer. What is 2 to the power n minus 2 to the n minus 2 count? So that's all in terms of bit strings. Okay, so if I know my bit strings of length n, I know that there are 2 to the power n of them. Right, that's the simple product rule. So now this looks like the complement rule where I'm subtracting something. Oh, yeah, well, I mean, it doesn't exactly unfold like that, but let's take a look at some of the options. The number of bit strings of length n in which the first bit is 0 or the last bit is 1. How many of those are there? Well, the or is again union. So if I count them, I'm going to use the inclusion exclusion, which does subtract something. So this might work. The first bit is 0. We'll call that A. The last bit is 1. We'll call that B. So we're counting A union B. Again, that's equal to A plus B minus A intersect B. So my A is that the first bit is 0. How many of those? Well, my first bit has been chosen for me. There's one way to do that. I have n minus 1 bits left that I choose either a 0 or a 1. So there are 2 to the n minus 1 bit strings that start with 0. The last bit is 1. Again, it's the same thing. I have n locations. The last one is chosen for me. The other n minus 1 locations, I have 2 choices each. So I get 2 to the n minus 1. Now, if the first bit is 0 and the last bit is 1, it's the same thing, except now I have 2 bits that are chosen for me, and then I have n minus 2 bits that I have to select a 0 or a 1 for. So yeah, then actually, well, if I add this up, this is actually 2 times 2 to the n minus 1 minus 2 to the n minus 2. 2 times 2 to the n minus 1 is simply 2 to the n. So yeah, that looks like number 1. It's not this one. The first bit is equal to the last bit. That would be, yeah, that would not quite be right. So yeah, you could do the rest of them if you wanted to, but it seems in this case we hit it on the first try. So yeah, that would be A. All right. Yep. The first bit is 0 and the last bit is 1, and the first bit is equal to the last bit. So the first bit in 0 and the last bit is 1 is just simply 2 to the n minus 2, right? This other one, C, I have to choose those 2 bits. So I have 2 choices for that, and then I have n minus 2 other bits to choose. So this one would be actually 2 to the n minus 1. Yeah, it's actually not that hard to count, I guess. But and then the number of bit strings where the first bit is not equal to the last bit, that's literally the same as the one above. If I choose the first bit, once I choose the first bit, I know the last bit. So I have 1 choice for both of those 2 bits. So there's 2 to the n minus 1 choices here. Yeah. Other questions? Okay. 100 students in this group, 63 students like beer, we'll call that B. 71 students like cider, we'll call that C. 25 do not like beer, do not like cider, so we know the size of B is 63. The size of C is 71. We know that this is not B and not C is 25. And we know that we have 100 students total. If we use the complement rule on not B and not C, well, the complement of that is, so yeah, the complement of that is 1 minus this set. But the complement is also, I can also write it like this, B and C complement. So these are equal. And then if I apply De Morgan's law to that, I get B complement complement, union C complement complement, right? De Morgan's law means I apply the negation to both B and C, and I switch the intersection to a union or vice versa. Of course, B complement complement is simply B, and C complement complement is simply C. So, and sorry, this is not 1. I'm thinking of, this is 100, right? So we have 100 students. I'm thinking of probability. So 100 minus B intersects C. Well, that's 100 minus 25. So this B union C is equal to 75. Okay, so now I have enough to figure out. What I want to figure out is how many students like beer and cider. So I want B and C, which I can now find out. I have B union C is equal to B plus C minus B and C. I can plug these values in, but first I'm going to, this is what I want to find. So I'm going to add it to both sides, and I'm going to subtract this from both sides. So I will have B intersect C equals B plus C minus B union C. All right, so then I have all these numbers, so I can solve. B is 63, C is 71, minus B union C is 75. So what is that? 59. Yeah, so let me see if I did that right. C, yeah, 59. Okay. Questions? All right. Okay, so bit strings of length n, where n is an even integer, and the positions are numbered 1 through n. So the number of bit strings of length n that have the following two properties: there is a 0 at every even position, and the entire bit string does not contain 1, 0, 1. So this is, we're now doing recursion, so I want to find, I'm just going to basically start building bit strings and see what I come up with, right? So I have, if I look at what my bit strings look like, there's a 0 at every even position. And n is an even number, yeah. So it would look something like this. Okay, so, and the bit string does not contain 1, 0, 1. So if I start with 0, then I know what my first two bits are. The third bit can still be anything. So the rest of this string is fine as long as it's free of 1, 0, 1. It has length n minus 2. So there's S of n minus 2 such strings. Or, every even, if I start with 1, then I know that, well, I cannot have a 1 here. I can only have a 0. And once I have a 0 there, well, I've decided, now I know the first 4 bits. So the rest of the bit string is fine as long as it doesn't have 1, 0, 1, and there's it has length n minus 4. So there's S of n minus 4 of those. So yeah, in this case, it would be D. And there's a lot of questions of this type, and that's basically it. You start building them and then see what the consequences are. Okay. Bit strings that contain at least one occurrence of 0, 0, 0. Let Sn be the number of such strings of length n. Which of the following is true? Okay, so 0, 0, 0. If my bit string starts with 1, that's okay. The rest can be whatever I like, as long as it's free of 0, 0, 0. If it starts with 1, 1, oh, sorry, at least one occurrence of 0, 0, 0. That's different. Yeah, so I don't care about 1, 1. 1, 1's already handled. 1, 1 starts with 1. So now it starts with a 0, 1, perhaps. And then, well, again, everything's fine as long as this has at least one occurrence of 0, 0, 0. If I start with 0, 0, 1, again, this is okay as long as it has at least one occurrence of 0, 0, 0. In the final case, I have, well, what if it starts with 0, 0, 0? Well, then I have at least one occurrence of 0, 0, 0, and these bits can be anything. Right? They can be 0 or 1 or whatever. I have n minus 3 of them, and n minus 3 of them and 2 choices for each of them. Okay, so then it would just be Sn minus 1 plus Sn minus 2 plus Sn minus 3 plus 2 to the n minus 3. And yeah, so that's B. Okay. Recursive algorithm, hello. This says hello 7. Because this is such a low number, I've shown you a couple techniques you can use. This I'm just going to build from the bottom up. Right, so I'm going to say H0 is the result of hello 0. And so I want to find out how many times the word hello is printed. If I give an input of 0, then I print hello once, and that's it. So H0 equals 1. H1 also equal to 1. If I give an input of 1, then I print hello once. So now I'm going to look at H2. H2, well, if n is even, H2 is even, then I call hello n over 2 and hello n over 2 minus 1. So that means this calls H1, so 2 over 2 is 1. 2 over 2 minus 1 is H0, so this is equal to 2. H3, so in this case, n is not even, so now I'm going to do the else case. In the else case, I call hello n minus 1 and hello n minus 2, so this is H2 plus H1. So this is 2 plus 1, which is 3. H4, this is even, so I'm going to call 4 divided by 2, which is 2, and then 4 divided by 2 minus 1, which is 1. This is also H2 plus H1, which is equal to 3. H5, this is H4 plus H3. So that's going to be 6. H6 is equal to, well, 6 divided by 2 is H3. 6 divided by 2 minus 1 is H2. H3 is 3, H2 is 2, so that's equal to 5. H7 is going to be H6 plus H5, which is 11. So yeah, that's another way. There's also, if you draw out the tree, you can do it that way. If you spot a pattern, you can use it. Sometimes these are Fibonacci sequences. This is Fibonacci-like, but it's not, kind of veers off a little bit here and there. So yeah, 11. See, yeah. We choose uniformly at random a string consisting of 14 characters where each character is a lowercase letter. The string contains at least one vowel. Okay, so what is the probability of A? So that at least one part means probably we want to use the complement rule. And if we look at our answers, well, there's a couple that use the complement rule. Perhaps not if the numbers are low enough, but basically A is at least one vowel and A naught is 0 vowels. And I know that the probability of A is equal to 1 minus the probability of A naught. And I can figure out the probability of A naught. So, so all of strings consisting of 14 characters, where each character is a lowercase letter. So that is going to be, yeah, and these are chosen uniformly at random. So this is simply the probability of some event is the size of the event over the size of the sample space. The sample space is all of the ways I can choose a string of length 14 from 26 characters. And the event is, well, the string contains 0 vowels. Now I'm choosing a string of length 14, but I have 21 numbers to choose from, or 21 letters to choose from, right? Because I've taken away the vowels. So this is 21 to the 14, which you can rewrite as 1 minus 21 over 26 to the 14. And yeah, so that looks like A in this case. Yeah. 11, 7 girls and 6 boys. Is this a counting one? How many ways? Yeah, so this is a counting question. How many ways can we arrange these 13 people on a horizontal line such that Eliza, who is a girl, has 2 neighbors, both of whom are girls? The order on the line matters. Okay. So what we're going to do is, well, there's 13 locations. Eliza must have a girl on either side. So, right, Eliza cannot be here because then she wouldn't have a girl on the left. So Eliza can start in location 2. Any of these locations in between, and if this is 13, again, I can't have Eliza on the end because she needs a girl on her right. So she can be anywhere from location 2 to location 12. So I have 11 possible choices for where Eliza is. So yeah, starting with the, so by the product rule, I have 11. So I'm going to choose a location for Eliza, and then I'm going to choose 2 girls, or, so, you know, if I choose 2 girls using 6 choose 2, then the order doesn't matter. But I do want to place 1 girl to the left and 1 girl to the right. I have 7 girls total, but minus Eliza, I have 6 left. So I'm going to choose the girl on her left. I have 6 choices for. The girl on her right, I have 5 choices for. At this point, I've placed 3 of the kids. So that means I have 10 left, combination of boys and girls, and they can go anywhere. So at this point, that's 10 factorial. So this looks like it would be B, 10 factorial. Or sorry, yeah, B, whatever that is. Yeah. Okay. Let X be a set of the numbers from 1 to 10. Choose at random a subset Y, where Y has size 5. Define the events. 1 is an element of Y and 7 is an element of Y. What is the probability of A given B? So I like to always start with the definition. The subset is uniformly at random, so when we're doing probability, it'll be the size of the set over the size of the sample space. So yeah, let's count these. Probably we'll start with probability of B. So 7 is an element of Y. So I've chosen, I know 7 is going to be in that set. So I have one way to choose that. So this is, well, first of all of the subsets of size Y, or sorry, all the subsets of size 5 from a set of size 10 is 10 choose 5, although this will cancel out. So the probability of B is the size of B over 10 choose 5. So counting B, I first choose my 7, and then I have 4 elements left, and I have 9 to choose from. Right, so I want to complete my set of 5 by choosing 4 other elements other than 7 from the 9 remaining. A intersect B is going to be similar. It'll be something over 10 choose 5. 10 choose 5. Again, though, these are going to cancel out. But so now we want the size of A intersect B. Well, it's the same essential process, except now I'm selecting 1 and 7. So 1 and 7 are in my set of 5. I need 3 more numbers, and I have 8 numbers left to choose from. So this will be 8 choose 3. So this would be 8 choose 3 over 9 choose 4. And if you have a calculator, you can just punch it in at this point. But I will do it, I will expand these binomial coefficients. This is 5 factorial over 3 factorial over 9 factorial over 5 factorial, 4 factorial. Okay, so the 5 factorials will cancel out. And then I'm going to invert and multiply 8 factorial over 3 factorial times 4 factorial over 9 factorial. The 3 factorial will cancel out with all except the 4, and the 8 factorial will cancel out with all except the 9. So I'll have 4/9, or is that one of them? No, that's a bummer. Did I do that right? Oh, sorry, I'm looking at the wrong answers. Yeah, 4/9 is C. I was looking at the answers to 13. Okay, good. So yeah, 4/9. But yeah, if you have a calculator, of course, at this point, you're basically done. All right. We flip a fair coin independently 5 times. The event, the coin comes up heads exactly 4 times, and the 5th coin flip results in heads. What is probability of A given B? Again, this is probability of A intersect B over the probability of B. Intersect. All right, so I flip a coin 5 times. Again, this is, it's a fair coin, and independently, the sample space is the number of different ways I can flip my coin 5 times, which is just 2 to the power 5 or 32. So this is going to be, you know, a uniform sample space on a size of 32. So now I want to count my sets B and my sets A intersect B. My set B is that the 5th coin flip results in heads. Well, that's fine. I know what my 5th coin flip is. The other 4, I still have 2 choices each. So that is 2 to the power 4 or 16. A intersect B, the coin comes up heads exactly 4 times, and the 5th coin flip results in heads. So counting that is a little more tricky, but not impossible. I have 5 coin flips. I need A and B to happen, which means the 5th one is heads, and A is the coin comes up heads exactly 4 times, which means that I have 3 other heads somewhere in here. So there's going to be 3 heads and 1 tail, and there are choose 3 ways to do that, or 4, which is 4 ways, right? So there's 4 ways to choose or 4 possible outcomes where I have 3 heads in the first 4 locations and the 5th is heads, right? This is, again, 4 choose 3. So 4. This is equal to 4 over 16, which is equal to 1/4. And yeah, it looks like D. Yeah, so D is the answer. Okay, 14. Let n greater than or equal to 3 be an integer. Consider a uniformly random permutation, and then define these events. Find out if they're independent or not. So they're independent if this is true. There's also other ways to define independence, right? If I said, I could also say, well, the probability of A given B is equal to the probability of A. But typically we go with this one. There are cases where that's easier. Okay, so what we want is the probability of A and the probability of B, and then the probability of these two. So probability of A is equal to, well, AN is equal to N. Well, we know the probability of B, right? We talked about that. We even said it's, by symmetry, it's a half. We counted the number of strings for which something like this was true. It was n factorial over 2. If I put that over the sample space, which is n factorial, I get a half, right? So the probability of B is a half. If you like, I can go through that, but hopefully that's, if it's a uniformly random permutation, then that's always going to be true no matter which 2 locations I'm comparing. AN is equal to N. Again, this is, I can go through it, but it's 1 over N. If I take any location, I could say A3 is equal to 1. That also has probability 1 over N. But let's sort of do it more formally. The sample space, all permutations, is n factorial. I take my last element, I put it in location n, right? I put n in location n. And then I have n minus 1 elements and n minus 1 locations. So this is n minus 1 factorial strings that look like A. When I cancel them out, I get 1 over n. Okay, so these are, you might see stuff like this. Any location, as long as it's a uniformly random permutation, any location equal to a specific number is 1 over n. I compare any two and say one is greater than the other. That is probability of half. Okay, so those are kind of gimmies. And now I want to see the probability of A and B. So now I have to, well, this is the probability of A times the probability of B is 1 over 2n. So let's find the probability of A intersect B. This time I'm going to, just for fun, but it really is, these are, independent. So yeah, the size of my sample space is n factorial. I'm going to choose to put n in the last location. Well, there is one way to do that. I'm going to choose, this is going to be a little messy. I'm going to choose two elements and I'm going to put the larger one in A2. Then I have n minus 2 elements left, and I have n minus 2 locations. Or sorry, no, I have n minus, I did this wrong. Because I have n minus 1 choose 2. And then I have n minus 3 elements left, right? So because at this point I've chosen A1, A2, and AN. So I have n minus 3 elements left and n minus 3 locations to put them. If I expand that out, I get n minus 1 factorial over n minus 3 factorial times 2 factorial times n minus 3 factorial over n factorial. All right, so this cancels with this. And then I get, so let's, now I'm going to rewrite this a little bit. N minus 1 factorial over 2 factorial times n factorial. The n minus 1 factorial is going to cancel out, and 2 factorial is simply 2. So I get 1 over 2n. All right. Again, if you have a calculator, though, you're one step ahead of the game. I mean, you can try it for small numbers, small inputs of n. So yeah, 1 over 2n here, 1 over 2n here, so they are independent. And of course, one way to think about it is, well, if I tell you A happened, does that give me any information about B? Well, no. As long as n is at least 3, then AN is not A2 or A1, so this gives me no information. I'm basically just looking at, okay, I know what the last element is, but I still have a string of n minus 1 that I got to permute, and this is still a 50-50 shot. All right. Another uniformly random permutation, 2 events. We know these are probability, or I guess told you that both of these have probability 1 over n. We've actually determined it, but yeah. So now the probability of A union B, that's equal to the probability of A plus the probability of B minus the probability of A intersect B. Okay, so probability of A, again, it's 1 over n. If I take any location in any number and say that location must equal that number, that is probability 1 over n in a uniformly random permutation. Probability of B, well, I've done the same thing. This also has probability of 1 over n. The probability of both of them happening, that is a little more complex. So I'm going to do that. Well, the size of my sample space is n factorial. I choose location, or I choose to put 1 here and 5 here. That's, I have one way to do that. And I have n minus 2 factorial elements, or n minus 2 elements left, n minus 2 locations, so n minus 2 factorial permutations. So this is going to be 1 over n times n minus 1. Right, once we cancel out the n minus 2 factorial. So this is 2 over n minus 1 over n times n minus 1, which is b. Yeah. All right. Question so far? Okay. 16, let A and B be two events in some sample space. We're given this, this, and this. All right, well, let's see what does that mean? Well, probability of A intersect B equals probability of, or sorry, A given B is the probability of A intersect B over the probability of B, which is equal to the probability of B intersect A, which is equal to, again, it's still the probability of A intersect B over the probability of A. So what does that tell us about the probability of A and the probability of B? So we know if I can get rid of these middle terms now. I know these two things are equal. And I know probability of A intersect B is equal to the probability of A intersect B. And yeah. Yeah, so this means probability of A equals probability of B. Okay. A union B is equal to 1. So let's draw a little. This is A and B. And if I take all of that together, that's everything in my sample space. So that's 1. And I know that these probabilities are equal. So now and the probability of A intersect B is greater than 0, which means that this is not empty. There's something in here. So what does that tell us about A and B? So let's say I divide this right down the middle. That means that everything to the left of this red line inside A is a half. Everything to the right is a half. Which means that if I look at A is 1/2 plus this, and B is 1/2 plus this. So yeah, the probability of A is going to be greater than 1/2. I would never ask a question exactly like this because D is also true. Yeah, so B is, I guess, more true, but yeah. If I asked a question like this, I would definitely make some changes to it. All right, questions? Consider a uniformly random permutation of the set 1 through 50. And then the permutation 8 and 4 are to the left of 1 and 2. So what is the probability of that? So probability of A is equal to, it's a uniformly random permutation, so something over the size of A over the size of the sample space. Size of the sample space is n factorial. And then I use the product rule to determine A. All right, so I have a permutation and I have 4 numbers that I have to place. So I'm going to choose those 4 locations. This is n, choose 4. Maybe there's an easier way to do this. Yeah, probably there is, but I'll go through the whole thing. So I've chosen 4 locations out of my string or out of my permutation. And then I'm going to place 8 and 4 to the left and 1 and 2 to the right. Of course, I could also do this, 4 and 8, or I can do 8 and 4, 2 and 1, or I can do 4 and 8, 1 and 2. As long as the 2 and the 1 stay to the right and the 4 and the 8 stay to the left. So I have 4 possible ways to do this part. Okay, so that's 4. And then I'm going to take, well, I have n minus 4 elements left and n minus 4 locations. So that's n minus 4 factorial. And then I'm going to, well, you would plug that into your calculator, but I'm going to say, well, n, choose 4 is n minus 4 factorial over 4 factorial times 4 times n minus 4 factorial. Oops. All of that is over n factorial. And then I start canceling. I have 4 over 4 factorial, which is simply 1 over 3 factorial, right? I just cancel the 4. 3 factorial is 3 times 2 times 1, which is 6. So this is 1/6. 17 should be D. Yeah, 1/6. All right, how are we doing? Yeah, I should speed up a little bit here. So I roll a fair red die and a fair blue die independent of each other to determine the random variables. Okay, so yeah. So I would, if it wasn't the dice, I would put all this in a table, right? If there's a smaller set. So here, each die though has 6 possible outcomes. 6 times 6 is 36. That's a big table. So we're going to say, well, we just want the probability that Z is equal to 2. So that means the minimum on my dice roll is 2. So that means either X is 2 or Y is 2, or they're both 2. And you know, if X is 2, then Y is maybe greater than 2. So we can just list out all of the, so we know our sample space, all dice rolls, all, you know, possible outcomes of a red and a blue die being thrown is 36. And then I just want to count Z, or sorry, this event Z equal to 2, which is equal to, well, let's see all the ways that I can have my red die be 2. So I can have 2, and let's say 2, 3. Let's say the Y is always going to be greater. 2, 4, 2, 5, or 2, 6. And then I can say, well, all of the ways that my blue die is 2. And then, of course, if they're both 2, I get this. So my size of Z is going to be 9. Or sorry, my size of Z equal 2 is going to be 9. Right? I can kind of list them all out in this case. So the probability that Z is equal to 2 is 9 over 36, which is 1/4. 18. Where did I go here? C, yeah. Consider a group of n people, and I want to be X is the random variable of unordered triples of people that have the same birthday. What is the expected value of X? Use indicator random variables. Right, so the problem is I have a room full of people, I take any 3 and I say, do you all have the same birthday? And you either answer yes or no. And I do that for all possible triples, right? And so my indicator random variable will be for, you know, for whatever 3 people I choose, that's either going to be 1 or 0. So Xijk is equal to 1 if Pi equals Pj equals Pk, where these would be their birthdays, and 0 otherwise. So now indicator random variables, there's basically 2 main questions you need to ask, right? So we're going to do, of course, we're going to use linearity of expectation. My variable X is basically equal to the sum of all of my indicator random variables. So when I determine the expected value of X, that is going to be the expected value of X1 2, 3, plus the expected value of x, 1, 2, 4, and basically all possible triples. Up to, you know, x, whatever it is, n minus 2, n minus 1, n. So because these are indicator random variables, the expected value of xi, j, k is equal to the probability that this indicator random variable is equal to 1. And what's the probability that it's equal to 1? Or what is that event? Well, that event is just whatever it is I'm trying to count. In this case, it's equal to 1 if these three people have the same birthday. So what I want to do is I have two tasks. One, because all of these indicator random variables are probably going to be the same for most of the, you know, I'm not going to ask you very complex questions. So this probability will be the same for all values, in this case at least. Maybe not, but if not, that it would still be really simple. So if I'm using indicator random variables, or I ask for indicator random variables, you need to figure out the probability that that event happens for each individual random variable. And you also have to count the number of random variables, right? Because E of x is basically going to be sum I, j, k, the expected value of x, I, j, k. And if I know this value, I can figure out this value. I just have to figure out how many times I sum it together. Okay, so I don't mean to drone on and on about the same points, but those are the two things that you have to determine for indicator random variables. So how many of these indicator random variables do I have? Right, I have n people and I'm looking at all triples. So I take all subsets of size 3 and I ask if you all have the same birthday. So how many of those are there? Well, I mean, there's hints over here too, eh? Yeah, so it's n choose 3. So the number of indicator random variables is n choose 3. In total, I just need to determine the probability that any 3 random people have the same birthday. So yeah, this is the probability xij k is equal to 1 is the probability that person I, person j, and person k all have the same birthday. The sample space is 3 people and 365 days, right? So I have, I choose a birthday for person 1, for person 2, and for person 3. And then the size of this event is basically all the ways that these 3 people can have the same birthday. So maybe they're all born on January 1st, or they can all be born on January 2nd, or they can all be born on December 31st. There's basically 365 choices for that. And I cancel that out. I get 1 over 365 squared. Okay, so those are the two main things. The probability, whatever you're indicating, the probability of that event, you have to determine. That's usually simpler than determining the probability of x's value. And then you have to figure out how many of these indicators you have. So here I have 1 over 365 squared times n choose 3. And if I look at this, that seems to be A. Yeah. All right, questions? Okay, yeah, we should get done. Consider a coin that comes up heads with probability 1/5 and tails with probability 4/5. You flip this coin twice. They're independent. Every time I get heads, I win $100, and tails, I win $50. And now I want X is the total amount of dollars that I win, and I want E of X. Okay, so there's a couple ways to do this. It's not hard to compute it directly using the the definition. I just have to figure out what possible values my K can take, right? So I can win $100, or I can win 50. So I can win 100 and 100, or I can win 150 and then 50, or I can win 50 and then 100, or I can win 50 and 50. So there's really only 3 possible values for K. Or we can use, let's continue with that. So let's say I flip the coin twice, I come up heads twice, so I win $200. And then the probability that X is equal to 200, well, again, that's just the probability that my coin comes up heads twice out of 2 flips, right? So that's 1/4. But we will come back to that in a minute. The other possibility is I win $150 times X equal to 150. Plus, or I win $100, I flip tails twice. So for, again, this is the probability that I get heads out of 2 coin flips. That has probability 1/4. Let's say this is heads. Probability of heads equals 1/4. This is the probability of, well, I get heads tails, gives me 150, or tails heads, which is 1/4 plus 1/4, which is 1/2. And this is the probability that I get tails, which is 1/4. So I have 200 times a 1/4 plus 150 times a half plus 100 times a quarter. That's equal to 50 plus 75 plus 25, or 1. Where did I go wrong? Oh, yeah, you're right. I got the probabilities wrong. Yeah, okay. So thank you. Let's change these probabilities. Heads with probability 1/5. So if I get heads twice, and it's independent, fair coin flip, it's 1/5 times 1/5, or 1/25. Heads tails is 1/5 times 4/5, which is 4/25. Tails heads is the same thing, 4/25. So this is 8/25. And then tails is 4/25 times 4/25, which is, what is that? 16/625, I think. Now I need a calculator. All right, I'm not going to compute that. So at this point, though, you could compute this if you had your calculator. I'm going to show you the easier way. So the other way I can do it is I can say, well, X1 is the money I win on flip 1. And X2 is the money won on flip 2. And then X is equal to X1 plus X2. And these coins are fair. It's the same. They're, again, identically or independently and identically distributed. So the expected value of X is equal to the expected value of X1 plus the expected value of X2. But X1 and the expected value of those are the same, right? The same coins. Yep. Oh, did I get? Yeah, you're right. Sorry. Yeah, thank you. Yeah, I'm the master of making dumb mistakes. So yeah, and I'm trying to speed up a little bit to get done, but yeah. So yeah, you could compute it at this time. I'm going to show you again the easier way. So E of X1 is equal to, well, I have 2 outcomes. I have If I flip heads, I win $100 times the probability that x1 is equal to 100, which is the probability of heads, plus tails, I win 50 times the probability that x1 is equal to 50, which is the probability of tails. So this is 100 times 1/5 plus 50 times 4/5 equals 20 plus 40 equals 60. So the expected value of any individual coin is $60. I have two of them, so it's 60 plus 60 equals 120. And if you did the math here, you would, I'm sure, get the same answer, unless I made another mistake, but yeah, 120. Yeah, okay. Given a fair red coin and a fair blue coin, you roll each die. Man, I'm frazzled this morning. Really, really looking forward to some vacation time. I roll each die once independently of each other. I, J is the outcome. I is the red, J is the blue. Define the random variables x equals I minus 1. Y are I minus j, and y is max ij. So here, if they're independent, I want to find two values, two events based on these random variables that are incompatible, right? So I want the probability that x is equal to j, or let's not say j, let's say k, and y is equal to L equals 0. And that these are actually possible. So if I can find basically two events, x equal to k and y equal to L, that are not compatible, then I can prove that these random variables are not independent. So let's say, well, I roll two dice. X can take on a value anywhere from -5 to +5. And y can take on a value from 1 to 6. But if I said y is equal to 1, then what does that tell me about x? If the maximum roll was 1, that means I had to roll 1, 1, basically, right? So that means I is equal to 1, and j is equal to 1. So that means x is definitely equal to 0. So what that means is that I can't have y equal to 1 and x equal to 1. The probability of that is 0. Yet, both of these are still possible, right? I have one roll for y, 1, 1. And the roll for x where I minus j, well, that could be 2, 1. So yeah, the probability of these two events are not 0, but the probability of the intersection is 0. Therefore, these are not independent events. Okay. Recursive algorithm, two tails, takes as integer positive, an integer k. All right. So I'm going to start running two tails with the value 1, and then x is the value of the output. So what is the probability that x is equal to 2m? So essentially, I'm returning 2 to the power of, well, each time I increment k plus 1. So basically, this is, I'm counting the number, m is the number of times I recursively execute this algorithm. Okay, so I flip a fair coin twice. If the coin comes up heads exactly twice, then I exit. Otherwise, I recursively call it. So I'm flipping a fair coin. I have heads, 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 tails, tails, heads, tails. Tails are the possible outcomes. Each has probability 1/4. and I keep running this algorithm until I get heads twice. Okay, so this is, I'm going to have some string of, tails, heads, tails, tails, heads, tails, tails, followed by heads, heads. So I'm going to have something, right? The probability of this event that I don't get heads, heads is 3/4. Right? So, yeah. And then the probability that I do get heads is 1/4. And M is the number of times I execute this algorithm total. So this means that this would be, I would have M-1 executions where I got heads, tails, tails, heads, or tails, tails. And then finally, I would get heads, heads. So yeah, it would be 3/4 M-1 times 1/4. Okay. Is the following statement true or false? Oh yeah, I wouldn't, I'm not going to ask you this question. Of course, for any two random variables, this is false, right? If they're independent, it's true, but there are examples where it's false. Okay, so let's look at this expected. Okay, so we're good. Eliza is a president of the Carleton Computer Science Society. She goes and has some drinks. So she orders 7 ciders, 1 cider at a time, and the server serves the wrong drink with probability 1/12. So we want to count the number of times that Eliza gets a cider followed by not cider. So the number of times he gets the drink right, followed by the drink wrong. Okay, so then in some sense, we could just say this is DI is not equal to DI plus 1. Use random variables. So XI is equal to 1 if they're not equal. So I want to count these events and 0 otherwise. So again, the two questions are, what is the probability of this event and how many indicator random variables do I have? So this is equal to E of x1 plus E of x2 plus E of x, she orders 7 ciders, 6, right? So we only have 6 indicator random variables because I'm comparing 2 consecutive ones each time. So I can compare 1 and 2, and then 2 and 3, and then 3 and 4, 4 and 5, 5 and 6, and 6 and 7, and that is 6 total. Okay, so that's the one trick, is that whatever I get for this probability, it's times 6. The other is that I need to determine this probability, which is the event that, well, for any I suppose, the event that DI is not equal to DI plus 1. So this is, sorry, not even that, but DI is a cider and DI plus 1 is not a cider. So yeah. DI is a cider with probability 11/12, and it's not a cider with probability 1/12. Right, so this is simply DI is a cider is this, DI plus 1 is not a cider is this. So that's the probability, which is equal to 11/144. Okay, and then this is equal to I equals 1 to 6 of E of xi. So it's essentially 11/144 times 6, or 66/144. So that would be C. All right, so yeah, again, indicator random variables. You need to find this probability, and you need to count the number of indicator random variables. Those are the two important calculations that you have to do. All right, questions? All right. Okay, so that's it. Sunday, yeah. We're not writing on Sunday afternoon. Oh, I think, what do we do, Monday or something? I forget, sometime during the week. Unless you're in 2404, then we're writing Sunday morning. So yeah, that's it. All right, yeah, thanks for, getting up so early and coming out.